Okay. So thank you for coming back for day 2. Today we are going to, you'll have plenty of time to finish anything from yesterday and a few more problems from today. But let me just start by sharing my screen. Okay, so this is day 2. Yesterday we had a little bit of time to talk about why mathematical modeling is useful for cell signaling, in particular because pathways can get real complicated very quickly, or pathways require a network, or combinations, interactions, cross-talk between a lot of different pathways. And so math can help us try and understand some of these pathways a little bit better. So today for day 2, we're going to be going over network motifs. Again, it's mostly an intro to network motifs, so we won't be dealing with like super complicated networks, but you'll definitely have a feel for how these network motifs work, what kind of behavior we can observe, things like that. So just to get us all back into the space of writing differential equations, I just wanted to start with an exercise where we go back to the toy model that we saw yesterday and we write out the ODEs for this toy model. So you can take a moment if you want, and then in like, I don't know, let's do like 3 minutes, and then after 3 minutes we can go over them together. But you basically just want to write the ODEs for A, B, and C, D, E, and F. Okay, so this is probably the biggest model we're going to look at. Yeah, A, B, C, D, E, F. So we got 6, which means you should have 6 differential equations. And you can give the parameters, you can have these as the same parameter. You can give them the parameter you want, like K1, K2, K3, K4, whatever you want. Yeah. We'll just take a few minutes.
Is the second line a continuation of the first one, or are those?
No, these are 2 separate linkage classes, but you see A is here, A is also here, B is here and here and here. So you'll have quite a lot of pluses and minuses.
Okay.
Yeah. Sorry. Let me share that back up. Okay, we can go through the equations together, just so that we can move forward. Let me just share my screen one more time. And I wanted to show you where this toy model comes from. So this toy model actually comes from a paper by the Shinar-Feinberg group. And in this paper, they actually go through all of the theory that you would ever need for, basically all of the theory you'd ever need for chemical reaction network theory. And you can kind of, here's the toy model here. They describe a lot of things that we're not going to cover in the class, like rank and deficiency theory. And deficiency basically tells you a lot about the stability of a system. But that's something we're not going to cover today. But you can learn a lot more from this paper and from a different one. And I'll put this in the Google Drive so that you can read it if you want to learn a little bit more about this specific toy model. But I wanted to make sure that maybe we can go over the differential equations ourselves. So I'm going to try and share things that I do by hand. So I wrote them. There we go. You guys can see that, right? In person. Okay. So I kind of wrote them on the side, but we can start over. So essentially, let me just change colors really quick. I don't think anyone has anything against purple. So if you wanted to write the differential equation for A, we would highlight all the places where A is. So A is here and here. So in this first reaction, so I just labeled them K1 and K2, like the top and the bottom. But you can name them whatever you want. You can go alpha, beta, whatever. I just did K1 because I thought it'd be easier. Okay, so here we are losing, because it's the forward reaction, we are losing with the coefficient of K1, and we're losing 2 A's. So A times A would be A squared. And then we're gaining A, so the reverse reaction, we're gaining A, so that's going to be a plus with a coefficient of K2, and we're gaining it from B. Okay, the other place where we see A is this reaction at the bottom, this one. And there's only one arrow, so it's only a forward reaction, but we're gaining A. So if you gain, it's going to be plus. So we're gaining A with a coefficient of, and I called that one K7. You can call it whatever you want. We're gaining A from B, so B squared. Oh, and then we're also losing. So there's this downward arrow. So that means we're losing with K10, we're losing A from sorry, we're gonna lose A and it's attached to an E, so we have to multiply it by E. Did I miss any other A's? No, I think I got all the A's. And you would just go through all of the variables like that. So like B is here and here and here. Yeah.
So now once A plus B goes to F, we see that there's a loop there. F is going to go to 2A, and then that is again going to feed back into the A plus B. You have to consider that loop.
Say that one more time. There's from here to here.
Yeah, no, from A plus B to F, the K10.
From here, oh, it goes like this and then back around.
Yeah, you have to consider that loop when you take into account that node A plus B.
Yeah, so the only node, like, so here we have this, oops, sorry. We have this arrow that's attached to A. These arrows are not attached directly to A, so you wouldn't have to add, you know, you're not gaining A from the K8, K9 reactions. Like you wouldn't have to add them to A because they're not directly adding, you're not gaining A from that reaction. You know, you're gaining A from the K7 and the K10. Does that kind of make sense?
Yeah.
Like in terms of the
irrespective of K8 and 9, the concentration of B and K7 are the only two.
Yeah, exactly. Like this arrow and this arrow. Yeah. Mm-hmm. Okay, but that was just basically so that we could just remember what the differential equations kind of look like, what how we use them and everything. But yeah, there's the paper for you if you want to look at that later. Okay. And you're free to, I think at some point in the problem sets, we'll come back and like actually plot this in MATLAB. I forget, I'll have to look at them. Okay, but for today, what we're going to do is talk a little bit about signaling pathways and how we can model some standard ones or some simplistic ones. We'll take a break and then we'll come back and do a little bit on network motifs. And then after the break, you'll have plenty of time to go over any of the problems that we've done up to this point and the ones on the problem sets, which I think there's only 3 problems. Okay, so what we're going to do today is, you know, model some simple signaling pathways, plot them in MATLAB, write and solve our own differential equations for network motifs. Okay, so like we said at the beginning, signaling networks can get really complicated very quickly, but we can still learn, you know, I believe we can still learn a lot from some simplified versions of them. For example, in the androgenic signaling network, there's a lot of moving parts, and that's essentially how cells work. You know, there's a lot of moving parts, there's a lot of things happening simultaneously, but we can still learn something if we focus on, you know, some of the key players or the big aspects of the pathway. But hopefully I can convince you that you can also learn something from a simplified version of a signaling pathway. But for those of you who maybe are not too familiar with the signaling pathway, it's a way for, it's one of the techniques or tools that cells use to respond to either internal or external environment changes. So like the most simplistic form, or like the biggest picture I can give right now, is that if there's a signal happening either externally or internally within a cell, there's a receptor, usually at the membrane, that will bind to that signal. And then from there, we get a cascade, the actual transduction cascade that goes through and, you know, kind of tells the top layer all the way to the bottom tier that there's some kind of a signal coming through until a target is reached. And then once the target is reached, the appropriate target is reached, then there's some kind of response, whether it be, you know, altered metabolism, a different gene expression profile, or even cell structure, mobility, cell life, or like cell division or cell death. These can all be, in theory, regulated by a signal transduction. And cells use, there are a lot of different mechanisms that cells or signaling pathways use to transmit these signals. One that's like very interesting is like scaffolding. So like a scaffold protein is usually a larger protein that binds to different parts of like the same pathway, in theory, to like help them find each other faster or to move them all where they need to be. So scaffolding is one way of transmitting a signal. There's ligand binding, like a lot of you might be familiar with ligand binding, protein binding, two proteins that need to bind together to either form a new complex or get some kind of job done. And my personal favorite, I spent 6 years looking at this one, post-translational modifications, which is, once the protein is out and about, it can be modified, and that can lead to a different response or some type of activity. And even in post-translational modifications, we can have multi-site modifications, like more than just one modification. And there's also docking, which we're not really going to cover today, but it's an interesting aspect of modifications. Okay, and there's a ton of different modifications. We could have phosphorylation, which is one that is kind of commonly taught. There's ubiquitination, in which protein can get tagged for degradation. Proteolysis, where a protein is broken down into smaller components. Methylation, which is the addition of a methyl group. There's a lot of modifications that can take place, but it's these modifications that lead to some kind of altered response, which could be, which we can think of as like the bottom tier of the cascade or of the signaling pathway. So for example, in breast epithelial cells, a growth factor will bind to HER2, and that will activate the RAS or RAF cascade, which deals with phosphorylation. So like RAF will activate the MECs, or like MEC1 and MEC2, and those will then activate the MAP kinases, like ERK1 and ERK2, and it's these transcription factors that can lead to cell division, which is why when there are mistakes in the way that this pathway is regulated, there can be an overexpression or an overactivation of ERK1, ERK2 that will lead to uncontrollable cell division, which is what's happening in breast cancer. So you can see that the way that a pathway is regulated can be very important. So if we can keep track of all of these proteins, or if we can determine how active they are or when they're activated, what parameters determine the activation of certain proteins, we can understand something about disease or about the way that cells just communicate within themselves. Okay, so this leads to the MAP kinase cascade, which is considered by a lot of people one of the most simplistic cascades, because there's really 3 types of proteins. There's the MAP kinase, the MAP kinase, which are the MECs, and the MAP kinase. And the MAP kinases are very, I hate using the term, but it's a promiscuous protein, and it will go through and it can essentially phosphorylate or activate all kinds of different proteins. So the MAP kinase cascade has a lot of crosstalk. So there's a lot of other signaling pathways that talk or communicate with the MAP cascade. So I figured for today, for the purposes of today, it's a good one for us to look at. So how do we model this very simplistic MAP kinase cascade? How many nodes and species do we have? So we have 1, 2, 3 species, which makes it a 3-node pathway. So we can actually write the ODEs for this one, and you can just give MAP kinase or MOS its own variable, like A, if you want, or M3. Same with the MECs and with the MAPKs. So just take a moment to write the ODEs for a single reaction with 3 different species.
would we do variable or species for each state? Or is
Yeah,
this
you
like-
can have, like you can just call the top one A and then a parameter for the reaction, the reaction rate parameter. You can call MAPK K2 or like, you can call, sorry, you can call like A, B, C, and then K1, K2, something like that.
Okay, so we're not modeling the two. like
No,
the-
not this side, sorry, not the right-hand side, the left-hand side, the one in the box.
Oh,
Yeah, sorry.
but still it's going, so the map, it is going to phosphoric map. kind of
Right,
thing.
we're not, yeah,
So
that's
we
this
will-
side. No, I'm talking just A to B to C.
But because this is not like, the first protein is not getting converted into the
Right.
second one, so there will be no change.
Yeah, so we're gonna go through, like when two proteins bind and actually do something to change the substrate. Here we're just doing like A to B to C, like you're gaining B from C because C did a job. That's what I mean by like the most simplistic
Are
form.
we assuming the red is lost when the green?
Yeah, that the red did its job and now we're in the MAP kinase. Yeah. Okay, does anybody need more time to just look at the ODEs? I can share mine. So I just wrote them by hand, like, there we go. So I just replaced just the variables and then just K1 and K2 for the actual reaction. And I can do this again. So for A, we're only losing A, and this would be a first order reaction. For B, we gain we gain B from A with the reaction rate of K1. So you can call it something different. But we also lose B with the coefficient of K2. And then finally, we're only gaining C or the MAP kinase. So yeah, as it was brought up, this is assuming that once MAP kinase has done the job, it's basically completely consumed by the MAP 2K. But we will go through examples where we don't do that, where we actually look at the process of an enzyme binding with the substrate and then doing something to give a new, like where the substrate is now changed. So yeah, we'll definitely go over that. This is just like the most simplistic version that we can think of for now. But yeah, we'll definitely be building up. So let's go back. Yeah, I'm switching screens a lot because I want to write by hand some of the stuff, and so it's on the iPad. All right. Okay, so let's just take some time now to plot it in MATLAB. You're just plotting the one that you the differential equations that you currently have for each species, and then just take a look at them, and then we'll kind of keep referring back to this one a little bit, so you'll see it again. So let's just take, I don't know, 5 minutes to do that. I'm gonna pause the recording. Yeah, I'm gonna pause the recording. Okay, now that we're back, I just wanted to share my plot. And then we'll do that, and then we'll take a break, okay? So I had the initial conditions. Let me change it to 1. I let K1 be 5 and K2 be 1. We'll play around a little bit. I just wanted to show you what my solutions look like. So it looks something like this, where we start with everything in the map 3K, and we kind of very quickly lose it, and that is probably because K1 is kind of big. But we get the map 2Ks, or the blue one in this case. I should probably make it not dashed. And then at some point we start to lose that one because it is now being converted over into the active map kinase, which is the black one. But if we change these around, let's make them the same. What do we see? Interesting. So you can see that we get the map kinase a lot faster now. So it's, and that makes sense because K2 was the last arrow that went from map kinase into the map kinase. You can also make these, like decimals. Like you don't have to always do whole numbers. Let's make it 5. And you can see that we might need a lot more time. So you would just increase your time. Let's increase it to, let's just do 20. I mean, MATLAB can handle it. Okay, and you can start to see some very interesting behavior. And as you can imagine, this is why when you are doing your own modeling projects, there's a full section of just parameter sweeps, because you don't know how these parameters are actually going to affect the overall response. That's why we need it. Okay, so let's go ahead and take a quick break. Yeah, I have a break after this, and then when we come back, we'll come back to network motifs. So let's come back. Hold on, what time is it? 2:11. So we're 10 minutes. Okay, we'll come back at 2:25. So let me pause the recording. Okay, I should probably give it another minute. Should I wait for stuff? Should we wait? Oh, there she is. Okay. So where were we? Here we go. Okay. So we looked at this one. Hopefully everybody got a similar looking plot if you used the same parameters as I did, which were 0.1 and 0.5 with initial conditions only for map kinase. But if you change your parameters around, you can see other interesting behaviors. All right, so then we took a break. Okay, and now that we're back, one of the things that I wanted to cover were network motifs, which you hear a lot about, and I remember thinking that I didn't really understand what they were, what they meant. So just a little tiny bit of, even more need for them, and why we should want to understand them is because, again, when you have complicated signaling networks, you're going to have things like promoter binding, protein modifications, other proteins binding, gene expression, gene regulation. You have a lot of these things happening, but they're interconnected. So maybe if you have gene expression that in turn influences promoter binding sites, there's a lot of things that are so interconnected that we need feedback, or we need these network motifs. So just a little bit of history. Move this. In 2002, Dr. Yuri Allen, I hope I'm saying that right, he asked if a real network differs from a random network when we're looking at subgraphs. So networks were these types of graphs, like connected graphs, where each sort of dot represents a node. So you can kind of see the language is going to be connected. If you have nodes that are connected to other nodes, you can have this network of nodes that are connecting to each other or talking to each other. But can we learn something about this real network if we're only looking at a sub piece of it? So for example, here, this graph is a subgraph of this more more complex one. So you can kind of see, like, if we have a super complicated signaling pathway, can we learn something about it if we're just looking at a subgraph, which is kind of like the whole point of today. And he wrote a lot of papers with multiple, with other great groups, where they actually were able to learn a lot from building these network motifs. Even for example, in this paper from 2002 about like the blocks of complex networks, they were able to learn about the transcriptional regulation of E. coli. This was back in 2002 as well. This was like a Nature paper, and you can see, like, if this is the real network that has all of these nodes, the edges represent the actual like line. Self edges would be when a protein like for example, a node that interacts with itself, or when we can think about it as like a protein that talks to itself or gives positive feedback for like auto-regulation for itself. And he compared it to like a randomized one, and he was still able to learn something pretty cool, or like try and simulate some of the growth for bacteria, or specifically E. coli. So you can read these papers as well if you are interested in learning a little bit more about the theory as to how these networks came about. But for today, we're just kind of go over some of the properties of these networks. For example, autoregulation. You can have positive or negative autoregulation. In negative regulation, what we see is that it kind of speeds the response time. We can reduce variability between cells of the concentration of this one particular protein or this one particular item that you're looking at. Doesn't always have to be a protein. It could be like mRNA transcripts or something like that. It also makes the input function more graded, or more hyperbolic, not like linear or more hyperbolic. For positive autoregulation, it can actually slow down the response time, and we can even get bistability. So we looked a little bit about stability analysis, where we set the derivatives equal to 0, but you can have two solutions come out of that, not just one. So like in this particular graph, if we look at just a time course or like a time course plot, you can see that negative regulation has that graded look, that hyperbolic look. But if we have no autoregulation, the negative autoregulation is more graded than if we had no regulation. And the positive regulation has a slower response time because it takes more time before we can see like an increase in that concentration. That's sort of what it means to have a slow response time. Okay, so what I wanted to do is to look at the differential equations for these motifs, specifically for positive and autoregulation, because I think these are the more common ones. And yes, I know they look a little frightening, but if we just go over it, I think we'll be able to understand them. So if we look at positive autoregulation, if we're looking at the differential equation for y, so how much y do we have over time? The graded aspect comes from this equation here. If you remember having, these rational expressions or rational functions, but we still lose a little bit of y from the response from the regulation. Like if there's you gain y, but you can also lose y. And even in the negative autoregulation, like the more important part to notice is the numerator for the graded aspect, or like the rational expression. So in positive regulation, you have, the concentration in the numerator and the denominator, but in negative regulation, you only have it in the denominator. So that kind of gives that that sigmoidal feel, that like the hyperbolic function that we had at the, like yesterday when we did the foundations, it was like 1/1 plus x. That's what this one kind of looks like. So the differential equations look something like this for positive and negative regulation. So we'll be referring back to this specific small table because for when you're building your own or in the examples that we're going to be doing. So we're going to do them in a little bit. Yeah, go ahead.
Is there a way one can get to these equations from looking at the scheme like we did before for the?
Yeah, so normally we wouldn't have this part. This was sort of developed from like the papers.
Oh,
Yeah, because of the way that the, where is it? The response functions look like. They were able to like develop the theory for it. I remember that I learned it once, and I should go over it. Like I can go find the actual derivation and put it up on the Google Drive. Like it's just a short or like a short PDF
but
where you can
it's
see.
not something we would be able to intuitively write down like we did for the.
Right, like when we look at this, it looks like a zero order,
Yeah.
right? But it's not really zero order because you have y influencing y. So yeah, you get like it's a tiny bit more involved, but it just requires like a little bit more algebra. It's nothing too difficult, but I can put it up on the Google Drive.
So the P is that probability or is it a rate constant? Like, you just use P as a.
This is actually I think it turns into P max, like the maximum y you can ever have. So it's like a parameter. It's the K that's the reaction rate parameter. Yeah. Which is why I'm like, it's like a tiny little bit of algebra, but it's nothing too difficult. I can put it up on the Google Drive so that we can all look at it and see how these equations actually came about. Okay, so if we just wanted to plot positive and autoregulation, we can have MATLAB do it because we know what the differential equations look like. So let's go ahead and do that. And you can do it on your own or you can follow me if you want. So I'm going to switch over to MATLAB really quick. Okay, which one am I doing? We have P, R, and K. So we have 3 different parameters and Y and like only one species, you know, because only Y is autoregulating itself. Oh wait, I already did it. Okay, I'll just give you a minute. You don't have to look at that. I'll just give you guys like, I don't know, like 3 minutes. Okay, from here until the end of the workshop time, we're just going to be working on those problems. The problem sets, let me just share them back up. So these, you know, we did most of these together, like 1 through 3, we did those together, and then 4 and 5 are for you to do today. But you can go back and do anything from yesterday as well, like any of these problems from yesterday. You're free to do any of those, and I'll be here to answer any questions. Again, if you want to be in a breakout room with other people, I'm happy to put you in there. Those of you here can work together in groups. Or if you would rather work on this on your own, you do not have to stay until 4:30. You are free to leave whenever you want. And I'll see you tomorrow if you don't stay. Otherwise, I'm here to answer all your questions, anything that you need help on. So let me stop sharing and yeah, let me know if you have any questions. And stop recording now.